Am I audible to you? Dear participants?
Yes, sir.
Am I audible?
Yes, sir.
Thank you. Good morning to you all. Namaste.
Good
Hope all
morning,
is
sir.
well. At the outset, I extend a very warm welcome to all the participants who have joined this webinar and deep regards to our research person, Dr. Manmohan Kaur from IIT Patna. I welcome you, sir. It is a matter of great pride and privilege to inform you that the college is organizing a series of webinars to keep up the academic tempo during the period of COVID-19. It has been organized by different departments of the college, and now today is the webinar being conducted by the Department of Physics of our college with Professor Prasanna Kumar Jana, head of the department, as the coordinator, as the convener, and other staff members are there. We are in constant touch with the academic community. The college is 56 years old with autonomous status conferred in 2014. The college is twice NAAC reaccredited, and we are preparing for the third cycle reaccreditation by NAAC. With IDP assistance from Government of Odisha and our commitment to science education in this college, the college is selected under Star College scheme of Government of India, Department of Biotechnology. We are planning to have series of invited lectures, number of webinars, and to listen from the experts to develop the academics, the teaching, learning process, and also to go beyond that. The objective is to develop, to improve the process of teaching and learning among the science students in the rural areas where the college is situated. It is in view of that, the college has chosen Dr. Manmohan Kaur with PhD from IIT and working in IIT Patna, having long experience in teaching, research with more than 100 international publications, is young scientist awardee, reviewer of reputed journals, conference organizer, and a strong academician. I hope that the session will be more interesting, more brainstorming with enriched ideas. The topic of today's webinar is quantum confinement and its application in technology is more scientific and subject-based. And I hope that all the participants, through interactive session, they will learn a lot, and it will also help the students who are undergoing either undergraduate or the postgraduate study. My heartfelt thanks and deep sense of gratitude to Dr. Kaur for accepting our request and sharing his views. Once again, I welcome you, sir. I welcome all the participants. Now over to Head of the Department of Physics, Professor Prasanna Kumar Jana, to give his address. Thank you. Thank you all.
Good morning to all. Am I audible? Honorable Principal Dr. Umchandra Pati sir, esteemed resource person Dr. Manoranjan Kar, respected teacher, those who have participated in the webinar, and my dear students. It is my proud privilege to extend a welcome to you all to this webinar on quantum confinement and its application in technology. We feel extremely honored by the presence of Dr. Manmohan Kaur on this occasion as his person. It is a matter of great pleasure for all of us that we would find time to be with us in spite of his busy occupation. This source is interest in academic and scientific pursuits. His presence here is a source of inspiration for all the rural research to the entire scientific community. I extend a very warm welcome to Dr. Kaur. Dr. Kaur started his career as Assistant Professor of Physics at TIIT Bhubaneswar from September 2008. After completing his MSc Physics from FM College Bhubaneswar in 1998 and PhD from IIT Guwahati in 2004. Then he started his new career at IIT Patna from 10th December 2008 to 16th December 2015 as Assistant Professor and Associate Professor from 17th December 2015 to till now. In his long career as a teacher, he proved himself as an excellent teacher and guide and a good administrator. He is awarded IIT Best Teacher Award in 1995-2018 and here is IIT Teachers Award and Dept Young Scientist Award. He has reviewed more than 30 reputed journals like JP, APS, etc. He has more than 110 publications in international journals. Dr. Gaurav has presented valuable knowledge in more than 70 national and international conferences. He is a member of 30 academic committees and he has completed 5 research projects and 2 ongoing projects in his lab. 8 scholars have completed their PhD under his guidance and 10 scholars are on the way. Dr. Gaurav is not only an excellent scholar, but he proved his administrative efficiency in the different institutions. Sir, welcome to our webinar. I take this opportunity to extend a warm welcome to our principal, Sir Dr. Webinar-Phy has extended cooperation and guidance. We are very much thankful to our respected principal sir for his encouraging and inspiring attitude to organize this webinar. Last but not the least, I would like to thank all the teachers, students, and all staff members of my college who have always been proactive, hardworking, and dedicated to make every event a great success. We are extremely hopeful that this webinar is going to be a great success and we request for your support to make it a memorable and successful event. Thank you for all. I request Professor Karan to deliver his speech.
Good morning. Good morning. Sir, am I audible?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine.
Moderator wants to do.
Hello. Sir, slide is visible.
No, sir. Yes, sir. Yes, sir.
Okay. Fine. So, can I start now?
Yes, sir.
Okay. Thank you very much. Good morning to all of you. So some background noise is coming.
Please, all the participants mute their mic. Please.
Okay, fine. Thank you. Good morning. Sir, please inform me if you are not able to listen anything. So please inform me immediately. So because I cannot observe it. So good morning to all of you, respected principal sir, HOD, and my dear teachers, and most important is my dear friend students. So when my teacher called me and asked that can you share some thought, whatever you have gained, and I feel privileged. So I had given some of the topics that they choose that the quantum confinement and its application in technology because this word is very catchy. So I will discuss on it, and please believe me, I will not take you to very difficult mathematics or something, and it will be totally informative. So in this talk, and this quantum confinement, exactly what it is doing and how we realize, and basically what is the confinement exactly we have to look and how we have formulated. Then at the end, I will give some of the examples. So before going to the talk, I will show you that means where I am sitting, and generally when I go for the talk, first I gauge the audience that exactly what level they want my speech and or they can listen me, but unfortunately I cannot see, so only I got some information from my teacher, so they say, and accordingly I'll proceed. And please excuse me at the end if I cannot pass any message to any of you or some of you. So with that, and let me start the topic, that is quantum confinement and its application in technology. So basically this is IIT Patna, and if anybody has visited, will see, and the top is our entry, the next is our science building where we sit, and this is some of the equipment of my lab that in the last we have developed, and we're doing some research. Please don't be very sacky that looking to that very big lab, and it is just part of my lab. I have not given all the figures and so many equipment. Basically, I am very totally an experimentalist, and it is scattered from behavior of the electron to understand the behavior of the electron inside the material, from starting from resistivity, susceptibility, or you can say that the size of the material, and etc. So this is the lab, and this is my current research highlight. Just I'm telling you that if anybody interested, and I can talk, and we have 2 patents already we have filed. So also we are interested in medical physics, and we do, and some composite materials, and etc. But today I'll be talking about the quantum confinement. It is related to my experiments like electron microscopy and all we are doing, that STM. So I'll not take you. So let me thanks to my students and my collaborators, as well as these funding agencies who has helped me a lot, and today I could do something in my life, try to contribute something, and also postdocs. And finally, I thanks to the Salipur College principal, head, and my teacher. Special thanks to my teacher Niranjan sir, and he was famous in the college in the name Niranjan sir. And basically, my physics career started from him only, because he was my guide in the honors. I transferred from some other college, and he was guide, and he was the role model. So from there only my physics career starts. So thanks to all of you, and finally thanks to the audience to spare your time to listen me. And this whatever I'm going to talk, please note down these references. And always as a physicist, always I request to my young student friends, please go through the textbook. Go through the textbook, which will take you to a height, or to make you understand the physics formulation. Only the textbook. So these are the textbooks which I have referred, and which means the topics. And if you want to refer anything, and you can look into these books, and you will be surprised to know these books. And my talk starts from here to understand these books are written by, if you look into the first book, it is written by a physicist, and the second book is written by the chemistry and biology, listen carefully, chemistry and biology people, and the third book is written by electrical and mechanical engineer, and the fourth book is written by again physics. So if you look into that, this book is written not only physicists, but also the biologist, chemistry and engineering. So by taking the help of this book, and I have prepared, or I'll be talking whatever I'll talk, and in the talk also you will understand that why you need to understand everybody what is the biology, chemistry, or nothing is this. So my talk plan is like this, and I will tell something motivation to the teacher, not very large and very small part, then the students to understand and this thing. So after that, I'll be talking about the basics and around 15 minutes that formulation of physics, how we have formulated, then we'll go to the quantum confinement and its application, then the connection of that physics formulation to the technology. So this please relaxed. Don't think that I will tell you say very big thing that which will be stuck in your mind. It will be very informative. Then if you want for a detailed understanding, because in the 1 hour I cannot give you everything, just it will be informative, so that you, if you don't try to understand that details, and you can definitely connect to my email ID, and generally I don't skip and I try my best level to answer and make on understand if I can pass the message. Okay, fine. So this is the motivation I told you to the teacher. We teach well because we do research. We teach well because we do research. That's what this is the slogan in the high reputed institutes in all over the world. What does it mean? The research, if you do the research, and really you believe me, what is that the student face the problem in his life from class 1 to 5, because that time he or she does not know anything. So after that, if your fundamentals are clear, then it goes on, and just you have to run your boat and remember and write and do your boat. But when you come to the research or the PhD, we have formulated in our modern language, it is the PhD, so that when you go to the research, really you have to generate. And but really, believe me, it is not difficult. It is the most easiest job. And the research does not relate to the big equipment, big computer facility, technology, etc. It is not related to that. Research is very simple. It is the observation and formulation. You can observe anything and you can formulation. In the next, I will tell to the students and what it is exactly. You just observe and formulate. So that's why it is the easiest job in the world. You can observe anything and you formulate it. Formulate means you make a common statement or a common equation which can govern your observation. So just recently I was reviewing and more than 5,500, and also from the Jagatsinghpur and Katak, mostly Ganjam, and those have submitted their projects, school projects, and I was reviewing around 5,500 projects I reviewed. And so in the DST, so that what government proposal is that this is the observation and formulation. One can observe in his village itself, can be in the family itself, and if some idea, good idea is there, and that government of India is trying to nurture, it is not only that you have to develop, everybody will have to develop the computer and mobile and etc. So interesting projects were submitted by the students. So government gives the money to execute it, and so just I highlight that means exactly what do you mean by the research and observation. A school student can do that, observation and formulation, that can be done. So that's what I request to my teachers and my community that you can do. So I've given the example what research a teacher, one example only, can be anything, teaching methodology, grassroots research, and etc. You just look into that. I have picked up a snapshot, and he's one of my friend. He's in NIT Nagpur. So after doing the PhD with me, and he did not get the chance to do the research. He was an optics researcher. So you will see that he is writing beautiful articles in teaching methodology. And don't think that, okay, I will not get the recognition and all. It is not like that today. And I just give my CV that I have published more than 200 articles in the different places, but it is not that your article will be less designed. You see that this is, I have taken again in one example of a international journal where you can publish your methodology. You can publish this, and you just look into that reflection on failure, teaching research methodology. This is one article. It is published in this journal. This is a also we publish in the similar kind of journal. It is, but it is a technological observation. But this is the educational observation. So a teacher can do and can write. It is not a single journal. There are hundreds of journals available, which has impact factor, which has ACI index, which has everything. So a teacher can also do if they don't get the facility. It is not that everybody has to be technology is only that what is looking the big equipment or the facility. So this is now for the students, and my dear students, please don't be hyped with the words that chemistry, physics, biology, all are the science, and they are the all are the observation and formulation. Either when you observe, either you have to formulate it in the language of chemistry or language of physics or language of biology, but the common language we take it is the mathematics. Then where the engineers and doctors stand, and basically your observation and the formulation of the science does by these three category professions, and that they take the language is the mathematics. Then where the engineers and doctors stands, basically they are the interface between the scientist and the common man. That's what it looks very high, but they also do the research. So research means only formulation and observation. Our ancient people were also doing, and same thing. So it is my request to the students here. So don't think that it is biology or physics or chemistry, and any profession you can take and you can do. And what is the motivation here? And my request is that please be focused. Be focused on your observation and formulation. If you are focused, nobody can stop you. Definitely you can. It is not that if I go with the computer science and I'll flourish. It is not like that. Everybody does the observation and formulation. Don't think that all computer scientists are earning so much. No. Okay. So I'll give example. You will see that if you say which educationalist or which professor or which technologist is earning the most, definitely not the Sundar Pichai. You will be surprised to know he is a physicist. Two physicists are earning the maximum salary today in the world, because those things are not highlighted. So if you are good, if you are focused, and definitely your aim will be fulfilled. So who are these? Alfred Nobel. If you look into the Alfred career, he has designed and he has given the memory device to this world. Nobody understand, he got the Nobel Prize, and after that he is getting so much royalty which cannot be comparable to any job salary. Sundar Pichai or anybody, it will not be comparable to that. Okay, another is your IBM researcher, the top researcher. He gets lots of money, and in the royalty and all is in the magnetic material. It is fine. So this is the motivation to the student. Please don't think that this observation and the formulation we do, because you have to do the societal work. That's what we call it is Parokar Swarga in Parapidakam. So that's what you have to do. It is the what is that problem? If you observe something, if you don't formulate, so how the others will understand? So that is the most important. So that is the two parts of my talk. I do it, and let us see that what we observe and formulate, we will understand. Then we'll go to the quantum confinement. If you look into the core, you see this is I've taken one example from that book only. So that is the example of that. What happens when you change the matter to the material? What is our observation? Our observation is that if you look into that in the low temperature or in the room temperature, some materials are solid. Solid means that you know it has a definite shape and all. Then when you heat it, it start flowing. That we call it the liquid. And very interesting definition is there, liquid. I'll not take there because this is not a talk and it will take too much time. And the gas, solid, liquid. Simple definition can distinguish all them in terms of the bond formation. So that the gas phase, Then gas phase means you cannot see the material at that temperature. That's all. We call it is the gas. We cannot see. That is our observation. Please remember, when I'm taking the observation, don't be hyped or don't be confused. I will clear you that what do you mean by the observation. So just next slide, I'll make you understand what is observation. So then it is the when you go more temperature, what happens? You will find that you are unable to stand nearby and something is happening. Or suddenly you will find that if your temperature is very high and there is a sparking in your electric plugs, why it is happening? Definitely some charge is in the space. So those observations, then we formulate, if you have a material, when you have the cold means it can be 0 Kelvin or it can be any Kelvin. All material will be solid at a particular temperature. It can be 0 Kelvin, you know, the Bose-Einstein condensation. So on that, everything will be solid. So, but some materials are solid even if at 1000 degrees, 2000 degrees, so depending upon the property. So then it is the solid, liquid, gas, and plasma phase we have formulated by looking the observation. You see, I'm telling you. Hello. 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 There is a background noise. Hello. Okay,
Yes, sir.
fine.
Start.
Yes, sir.
So please mute the mic so that I can speak. Otherwise, difficult. Okay. So that's what this is the formulation. Please understand that this is the formulation we have done by looking the observation. Okay. Repeatedly, I'm telling this because I'll make you understand exactly what do we say that observation. Then it is the formulation, and we'll come back. Now you come back. So if you look into the other side of a arts person or a culture person, and this is the basically the society what we do, also we do the formulation. It is not that only the formulation in the physics or in chemistry or in biology, but also there is formulation in society or also in engineering. So this is the societal observation and the formulation. So I hope I make you understand what do you mean by the observation. That we use the steel, so we call it is the edge of steel. We use the polymer, we call it is the edge of polymer. So that's what it happens, the observation. Now, the real understanding of the observation, you see that how beautifully science has given. And if you look into your quantum mechanics, always you write. Okay, in the quantum mechanical formulation, our first assumption is mass tends to 0, V tends to C. When we say the mass tends to 0, always in the basic question we keep on asking, what is mass tends to 0? What is that mass? Okay, please remember, once again I'm telling the observable. Please, you just look into the my glossary. I've written somewhere the human scale. So basically, observation is nothing but what we can see, we can observe. That is nothing but we call it is observable. So what I was talking about in the formulation, that we formulate solid, gas, liquid, and like that. Similarly, by observing that we say that it is the human scale, or we call it is conventional engineering, or we call it classical mechanics, or we call it the Newtonian mechanics, or we call it is the observable. We call it is the observable. Fine. So now, what I would like to tell you that please you understand this, how we have formulated. So if you look into that, there is a particular length scale where we have given the name. That is the astronomical scale and terrestrial scale and human scale, then molecular and atomic scale and subatomic scale. So just you understand what way you have looked into that 10 to the power minus 6 to minus 3, that is nothing but your human scale. What you can observe, you can understand, you can modify, that is the human scale. That human scale, we say it is Newtonian mechanics, or we call it is the conventional engineering. This is conventional engineering, or we call it is the observable. So when we say mass tends to zero, that is nothing but which cannot be observed by the human being, nothing else. Okay, so beyond our observation, or this classical, we call it is the observable. Not observable, we call it is the quantum, that is mass tends to zero. Please remember, when we give anything, what is the reference? Mass tends to zero, reference to what? Reference to our observation, classical scale. It is very, very simple. This is the human philosophy we have taken, and we write it. M tends to zero is nothing but it is your below the micrometer. It can be nano, it can be pico, or anything, but it is below the human observation. So very interesting. The science starts from there, which I am unable to observe, but I am trying to formulate that M tends to zero. Please remember, and I'll just do it. And basically, when we call it is that observable. So what happens? Just a minute. Just a minute. Hello. Am I audible? Hello.
Yes, sir.
Sorry, some disturbance. Okay, fine. So I'm sorry. So this is the observable. What do we say? Fine. So when you see the observable, basically what human can observe, can understand, that is nothing but our human scale. Then beyond that, we call it is the micro world. Please believe that we call it is the micro world. That is nothing but we try to formulate in that world. So that's what we call it is the all about the quantum mechanics. It starts from there in the quantum mechanical, and I'll make you understand here, then we'll take it. So when we say the classical confinement, and what we call, suppose you have I'm a human being, and classically if you want to observe, we write in the book, okay, I am a human being, I have the freedom, I can go anywhere in this world, so I'm not confined. But if I stay inside my room, that is, I confined inside the room. Like you are confined right now to this talk. So you have confined. That is nothing but you have polarized. So now you think a particle or anything beyond our observation. Are they exist? They exist. How they exist? Okay. So when they exist, definitely, and inside it we have formulated. Please, if you understand this formulation from classical observation or the classical thing, then everything is easy. So in the classical, our field is, I told you, our field is the earth, and I am a particle. But if you come to the quantum, in the quantum means your size of that is not no more, it is your observation. But inside it, again, we have formulated, there is this. And what we have done, okay, I'll come back that what we have done on it to formulate it. You see the physicist, and in the 1960, nothing was there. But this physicist could, by realizing this formulation and this thing, he said, and we have all the formulation beyond this human scale or the convinced route, but we have not done anything. So that you see this vision and could bring us this today, this quantum confinement property or the quantum mechanics by developing some equipment. This visionary of the Feynman, please don't mislead. This talk was and his statement was totally visionary. That what is the vision? Vision is that we have not done anything beyond the classical observation. We have not done anything in the beyond the classical observation. Let us start. So that's what he brought. He requested everybody, and people understand that exactly is right. So please don't feel that it is not basically we did not have such things. Just I want to make you feel that we have developed and day by day without this, and this is the ultimate aim, this your quantum confinement or the molecule and this thing. So we have to understand what you mean by the quantum confinement. Okay, so here if you look into this and you see that this, if you look, it is a butterfly, and you just look here and there, you will find that beautiful color. Believe till 1970, including Feynman and everybody, they were trying to explain what exactly it is happening. But in around 1900, people start talking about no, something is happening beyond our observation inside it. But people were trying to tell there are the pigment, there are the polymer, and those things, and so many thousands of explanation is there. Why butterfly wing is very color, or our leaf is very color, and why it is very slippery. So many questions were there, and before 1970, people were giving lots of explanation, but nothing was accepted because they were unable to formulate really. So the people thought, no, beyond the classical observation, something is there. So if you look, and you will surprised to know, it is the quantum confinement or limit of classical diffraction that is giving you the very beautiful picture here. You see, our physics formulation long back, if you look the quantum confinement, it was the de Broglie was in around 1920, and that time, since that time, formulation was there by looking the people, but people took lots of time to understand exactly due to the quantum confinement or the limit of classical diffraction can explain this beautiful color. We'll see that how it happens, it is happening. And in the next slide, if you look, and with the 1970, by looking to a very electron microscopy, people see interesting. It is black and white picture, because in the quantum world, it is 1 or 0 probability. We say it is probability. Formulation is simply probability. In the next, I will tell what does it mean. Then we come. So if you look into that, it is not a continuous feeling, not continuous belief. It is not continuous. Separation is in nanometer order. Then we found. So immediately people go back. You see, ray optics. I think Newton gave it in the long back, and formulation is there just by looking to the ray physics and your Young's formulation. If you look into that, you see that your beautiful light are reflecting from different places, and they form the interference and diffraction pattern, and this beautiful color comes. Why? Just you go back to the experiment in your BSc physics and Newton's ring, and it depends upon the thickness and depends upon your separation of air gap between the two plates, simply. So, but here, beautifully, these air gaps are different. So when the air gaps are different, your 2D sin theta is equal to L lambda, the master equation for your diffraction and the interference. So D is the thickness. Thickness will decide, and your wavelength should have the proper interference. Wavelength has to have the proper interference. That simple theory, our basic book physics, and could make understand why beautiful. And you will be surprised to know this basic simple theory or the principle has been taken the technology in a different height. Today you see your laptop, anything you see, very beautiful color, nothing. They have just controlled the film thickness, nothing else. By understanding this nature, they have only controlled the film. on the top of your film. You cannot see. That film thickness you cannot see because these are like this. You require electron microscopy to look it because it is not observable. Your optical microscope or these things are not, your eye is not sufficient to see it. So, but the modern technology or formulation is given. This is another example that we have demonstrated that if you change the size, this is our result and it is published, you can look into. So what happens if you change the size, what happens, it's observance wavelength changes. So here the formulation starts. These are our observation that I am illuminating with a particular visible light. Visible light is nothing but our observable. And we are looking at the same material. For example, gold supposed to be yellow, but you illuminate and it will be different color. So what happens to that level? And you see gold with the different size. You see it is also a beautiful demonstration, also another work of us, that how the particles are combining. Okay, combining. It is not that particles or atoms are coming, and it is a demonstration that how the reaction goes on. And if the particular size comes, confinement, particular size is coming, that is nothing but the elements are means basically confining. With this example, this is another experiment that beautifully you see that it is mapped. Can you imagine this is a experiment, and this means I have taken this image of your graphene. You see how beautiful it is there. But the question is that how the physics formulation is helping to these to understand this beautiful world, and today we are realizing. So that is the formulation of physics. Please, my dear student friends, please remember, never you ask to anybody what is an electron, what is an electron. If you ask anybody what is mass, so I think it is a debatable, it is difficult, because this is our formulation, these are our fundamental we have taken. So fundamental, like what is earth, we cannot say earth is earth, we are standing. So this is our formulation, this is our assumption. So similarly, entire world we have tried to formulate, listen carefully, by assuming there is an electron and it is a mass, it is a charge and spin. But definitely if you ask me, sir, what is the proton? I can explain. What is a quark? I can explain. But if you ask me what is an electron, I cannot. If anybody is saying that, okay, this 3 quark is electron, this is wrong. Because our fundamental assumption is there is an electron, and it has a charge and mass and speed. That derives everything. So if you ask me other things how to explain, I can explain. But if you tell me that what is electron, by taking the help of proton, if I say this is the electron, this is wrong, I cannot. Because proton is not a fundamental particle, it is not fundamental. Its definition has been given by reference to the electron. Okay, so similarly, the way I told you the classical mechanics, whatever you have the observation, classical observation, the fundamental is your quantum mechanics. Even if you are going to explain quantum mechanics, but your fundamental has to be have the observable, that is your classical. So that's what we call that quantum mechanics. That quantum mechanics, whatever formulation you do, but finally it has to be observable. So quantum mechanics, why we prompted to do it? Because we observe the spectra, nothing else. We observe the spectra in observable way. That means different kind of spectra we get. That's what we prompted, and today and after that spectra formulation we are doing a lot. So the electron, it has a charge, it has a mass and speed. And this formulation has entire formulation of the quantum mechanics or your material world or your earth is explained by taking this simple assumption that is the electron. And now the people are thinking if electron is it is a confined particle, it is a solid particle, independent particle, if it can exist, so definitely it will have the building blocks of some particle. Simply you think you are a human being, you have lots of molecule, can I take any molecule from you? No. Okay, so that's what you are solid. So this is the observable quantity. But if you keep on reducing, we have also lots of particles, smaller, human beings, smaller. Then that particle also exists. That virus is also exists. How we formulate? That is nothing but the electron. Okay. So what we understand from this just now, that we understand that if we cannot observe or cannot modify, that is not. Quantum is nothing. Finally, the classical observation. Okay, so basically in the quantum mechanics, what we do, what we say, either we explain. So any observable, you want to write a wave function, what is that? It is a function. So you observe in the experimental one by one, then you plot, you will find the function is plotting like this. So nothing else. It can be a wave function or it can be a spin function. Spin function is time dependent, and when you come to the wave function, we call it is a basically your space coordinate, depending upon the space coordinate. If I measure some quantity in different place, okay, in different place, I'll get a function. Okay, so if I plot it, then I get it. This is nothing. Don't try to visualize in the classical way that how this wave function is, it looks like, and this thing. No, nothing. It is, we have plotted and it is a wave function. So what is happening inside? Inside is only the energy level and all this. Only the energy level changes. So that's what I told you, that spin formulation, what we say, just in modern quantum mechanics we are changing. I will not take you to there. It has been changed that nothing is exactly spinning. So that formulation is coming up. So people are they are debating that it is not exactly spinning something. But right now, what is the formulation? You see that how the science is changing. Because the spin observations, people found that it is unable to explain only by considering it is electron is spinning. But till now, the test book has not changed. So let us only talk about the test book, the formulation. The most appropriate or acceptable formulation is that electron spin. What is that? With the time t is equal to 0 to infinity, if you measure, what you will get? You will get the value, momentum value, in such a way that if you plot it, you will find a symmetric. Okay, all you think about spin is only one line. So what it will happen? The top portion will be lying on the surface of a sphere. Then we call that, okay, you tell that with the time t is equal to 0 to infinity. Listen carefully. This is again probability that each and every point you can put it, that it will be happen that just I'm sorry, so I have to sign something. Okay, fine. So that's what we say, that the probability means 0 to t time. That means each time, infinite time, 0 to t. If you measure and plot it, you will get a spherical symmetry. That's what we see, that it is a plus up, minus up, and it does not have any particular up and down. And that to understand, we plot it, we just write in the test book, but exactly it can be anything, plus up, minus up. Basically, the direction will be different. So that is the unpolarized spin. So that is the quantum mechanical explanation. Please remember, never electron can be classical, because its mass length is no more in the classical range, and never you confuse. If anybody says we say that, means we say the semi-classical, semi-quantum. What is that? We try to adopt some of the classical concept or classical equation, then we call it the semi-classical, nothing else. But electron is quantum particle, we understand in our formulation. Never it can be, atom cannot be beyond 10 to the power minus 6, which we cannot observe. These are the quantum particle. Okay, so that's what we say. And already I told you that atom, each electron confined with the orbit. So let us understand the material by extending our formulation of atom. Atom, electron is going inside, so they are confining in the orbit. So if I have a material or a material of 10 nanometer, 20 nanometer, 30 nanometer, that means what happens to that electron? Let us combine and try to understand what happens. because electron in an atom, it is confined. Then again, electron in that material, in that length scale, it is confined. Also the electron in our body or in our a big material also confined in that length. Okay, so that I've given you that just assume that atom and the human being are a bigger material, what happens? Okay, so also I have tried to make you understand that if you just you think, if I take your leg or hand, this thing, what happens? You are no more free particle, free. You will just confine. Suppose your leg is not there, you cannot walk. Okay, you cannot walk. You confine. So that is the simple confinement. So similarly, the quantum particle, when you have a classical particle, when you have a classical observable, inside it, the quantum particles are confined within that boundary, and they form you a classical particle with a particular energy. You see that electron, same electron inside me, its energy is different because it is confined in this thing, and same electron in copper, it is confined in different way. So that's why its energy level will be different. Very simple, no difficulty. Okay, so energy level is only different. That energy level of what? Electron energy is different inside my body and inside the copper, but electron is same. Okay, so that our assumption, fundamental assumption is there. So now comes back, we will see that how it is very beautiful confined. Okay, so electron is confined in that length scale. I hope you understand this and clear, and I hope I'll finish it within 15 minutes, that to make you understand that exactly what is that. Very simple, de Broglie wavelength. I told you, see one example that how beautiful it is, the color of the bird wing. Sir, how much time I have?
Yeah, as you like.
Hello?
Go on.
Okay, fine. So de Broglie wavelength, let us see that what is happening to the de Broglie wavelength, Bohr radius, those things you have derived. Okay, when you try to explain, and you may have solved lots of problems, and you see the what it has happened to this de Broglie, and you see that the theory, Newton's corpuscle theory, hygiene of the light, then at the end, and the argument and the observation formulation, finally de Broglie write that lambda is equal to h by mv. Okay, you will be surprised to know today we have realized this equation experimentally. Okay, and if you look into that, it is the hypothesis and it is principle, but today we are proving, and maybe after few years or few months, maybe the people may say that it is the de Broglie law. It can, because experimentally we are proving, now we have the equipment. So that's what the talk I told you, that I will make you that how the simple equation, it took 100 years and to realize that this law, this equation has a very important in our practical field, because people are unable to do. So now you see lambda is equal to h by mv. I hope everybody knows. So if you calculate the wavelength of an electron, and I've written that if the velocity is 0.01 c, and compared to the light velocity, c is light velocity, m is 9.1 and 10 to the minus 31 kg, and lambda is equal to, this is just example how we calculate in our textbook what is the wavelength of an quantum particle, and also we have extended that. Okay, in the classically also we can find. So now you see the fullerene, it is a carbon 60 atom, carbon 60, and again another Nobel Prize went to this Proto-Smalley to formulate this carbon 60. Very interesting science or physics behind it, that how they got the Nobel Prize. And you will see that very, very simple, not very big, that they were trying that how we can accommodate the 60 carbon atoms, and with also, it is also quantum confined molecule. But what they did, they took the example from classical example, that is buckyball, your football, simply football, same football, and each node carbon they put, and they found that, oh, it is stable. They calculate the energy, they say that it is stable. So it is the structure. So don't think that they have done something different. They were trying modeling in the different way, but they could do it, and this helped. Football helped that it can be only this much. Okay, just to tell you that what exactly the people can do it, and you can observe and formulate in anywhere in this in any point of time. So this carbon 60 after formulation, and due to that formulation they got the Nobel Prize, but observation, all other observations were by the different scientists. So this carbon 60, if you calculate, then you will get something. Then now you the 2.5 picometer, you see very small. Then you calculate your wavelength in your body. But now you comes back the electron, you see that it is very simple. Electron inside the material. And if you have a semiconductor, let us calculate what will be the electron wavelength inside the semiconductor. Okay, so the data is given. So observation, that is 0.1 m0 rest mass of the free electron. Then if you take the velocity of the electron, it is 10 to the power 5 meter per second inside the semiconductor. Just calculate lambda. Lambda is equal to h by mv. Everything is in front of you. You know the Planck's constant and mv. You see that 73 nanometer. Very beautiful. 73 nanometer. What will happen? This is the minimum length in a material. Listen carefully. Minimum length material should be so that the electron can have this wavelength. Okay? Electron can have this wavelength. Suppose your material is below this. What will happen to the electron? It cannot make a wave. It cannot make a wave. Okay? So it cannot make a wave. So that argument, you see that in the beautifully this equation landed that, oh, this electron will confine. It cannot move. I hope I make you understand what I mean by the confinement. Nothing else. The subatomic particle and electron is confined in my body, but confined means it is making the wave moving from my hand to leg to this thing. But if you reduce the size of a material, you take a copper or you take a silicon, suppose it is 5 micrometer, then definitely, so if your this is a 5 micrometer, then electron can make a move wave inside the material and move from one place to other place. But if it is less than 70 nanometer, what will happen? It is confined. It is confined. It cannot make a wave. That is the confinement. I hope I make you understand what we mean by the quantum confinement. Quantum is nothing but it is a particle, quantum particle, and confined inside a box, and it will happen. So now you see that the electron inside the 70 nanometer semiconductor behave like the electron inside the atom. Okay, so that's what we call the atomic theory can be applied to this nanometer material. That is nothing but the quantum material. It is not the nano, it is quantum material. Why quantum? Because its length scale is below the classical range. That's why it is the quantum material. So inside the quantum material, who is confining? The electron and hole. And again in the hole, in the next you see, if you calculate lambda is equal to h by mv for the hole, then you get only around 20 nanometer. Okay, 20 nanometer. So now let us come to the material. Sorry, metal. So in case of the metal, and you know that its velocity is a little high, 10 to the power 6 or 5. So please don't take that in your textbook. You will have the Dept velocity, and don't confuse. These are the electron velocity inside the material, random velocity. It is not the Dept velocity. Okay, Dept velocity is totally different from this velocity. So this I'll not take you to there, but you remember that it is Dept velocity is entirely different from this. So that the material, and in the metal, when you see the electron velocity, it is around 10 to the power 6 meter per second, and its mass is effective mass, you know, it is close to the rest mass, and sometimes it is higher, it is lower, and so that's what inside the metal. So if you put it, and it's see value 0.24 nanometer, very interesting. This value has given the opportunity to reduce the size of the material. You see, this is a formulation. So what we control that we can, if we make a equipment below 70 nanometer of the semiconductor, you can confine the electron. Very interesting. When you electron confine, what will happen? Basically a particle inside a box, we have the quantum mechanical. So these are the data that are available. So anybody, if you want, you can refer and you can calculate for any semiconductor, and you can see that what is the confined length. I'll come back that single electron transistor. Go to the Bohr radius, we calculate. Never we thought, we say that in the semiconductor, we again would due to by this formulation, we say this weak confinement if only electron is confined. Then we say the strong confinement if electron and hole is confined. Then we say that intermediate confinement if only in electron confined, but hole is free. So semiconductor interesting. You can connect it that n-type semiconductor. You make it the quantum material. So what it will happen? It will become the p-type. You see how the interesting you can make the your technology. So that's why in the metal, if you go to a metal, and what I say that if you reduce and when they enter into the quantum regime, repeatedly I'm telling below the classical range 10 to the minus 6 microvolt. When they enter to the quantum regime, what happens? They behave in different way. Why? Because quantum confinement comes to the picture. Now you come to this, and you may think that it is very, very it's difficult to understand. No, everybody has gone through our basic book. What is that? In the back we understand particle in a box. What is the particle? Here particle is an electron or a proton. And what is the box? Your quantum material, length scale, that is either 70 or 40. It is a stable material. Okay, that is your box. So electron is inside. What will happen? What will happen? That is nothing but the quantum confinement. When the size is in the quantum range means repeatedly I am telling below the 10 to the minus 6, that is the beyond the classical range, and but they exist. I show you the picture, electron microscope we can see. So that's why the degree of confinement of the bulk material is 0. That electron can have a wave in any direction. So that's what we call it is the bulk material. Then quantum well, degree of confinement is 1. And that is nothing but the freedom is 2. That is nothing but your 2D system, thin film, whatever you are looking in the device. That is the quantum well. So you see that how the quantum confinement in one direction, all thin film we are using, nothing big thing, and all are the quantum devices. Whatever you have right now in your hand, all are the quantum devices because their length scale is below the observable. But observation is your classical. So nanowire, then you have the one dimension, the free, that is like a rod and this thing, and quantum dot, and it totally from all the direction it is there. But don't think that quantum confinement is always it is a sphere and this thing. It cannot. It can be in one direction. So what is the confinement? Basically what we conclude, the quantum confinement is nothing but the subatomic particle cannot form a continuous wave inside the integral to travel. Then we call it is the quantum confinement. What do we understand? So basically it happens the symmetry breaking, nothing but particle inside a box. Okay, inside a box, either one-dimensional box or two-dimensional box or three-dimensional box. So please connect to your basic knowledge. That is nothing but when you go, you write the Schrodinger equation, very interesting potential and this thing, then you solve it. Okay, if you solve it and plot density of states, what is that density of state? Very simple. The electron density at a different energy level, Why it is happening? You come back. Don't be confused that what is happening. So what it is happening, that if you observe or if you try to measure the energy of all electrons in a material, you will find of the electrons, no more it will be like the electron in an atom, no more. Okay, entire material will be behave like an atom. I'm not telling that it is an atom. It is like an atom. Entire material will be behave like an atom. So if, now you connect in the atom, the electron are in K cell, H cell, M cell. Same way, some of the electron will be at the ground state and some of the electron will be in excited state, some other electron will be in excited state. So you will get a distribution of electron in discontinuous way, and that length scale is nothing but your thing. So I'm not going through this mathematics. Is a very simple, and that you can find out any textbook that dE, that is the density of state, and you plot it, so you get that 3D, 2D, and 1D are different. So I'll finish. So that what happens, you see that these boxes are nothing but it is the quantum particles. You see color is different, but the atom, same atom. Okay, same atom, the color is different. Why it is happening? The electron is confined, so material. You see that what I was talking, atom, copper, gold, and they are the different atoms. But now, same atom, but they have formed the atom-like material, atom-like material. It is not that they are no more, they are the atom. So fine, so this, whatever I say, I told that whatever around you, you are seeing, and it is this quantum confinement has been used for you, either you may try to make a beautiful color, okay, try to make a beautiful color, try to, so those quantum effects are already everywhere and without common man. So I'm taking that where the people are using the technology, and this is the direct application of the quantum mechanics or the quantum confinement. Sir, how much time I have?
Subject go on.
Hello?
5 to 10 minutes.
Hello?
Sir,
Hello?
please go on.
Okay, 5 minutes. So this is a scanning tunneling microscopy. I will talk about it. You see, this equipment is available. By using that, I took it. You see there. Okay, you see there. You have a specimen. You have a sample.
Sir,
And
tell us
this,
the quantum key commonness.
sorry. Sorry. Hello.
Quantum key commonness communication.
Hello.
The scientist. Prashant.
I cannot hear you properly. Can I address this after the talk? Hello. Hello.
Okay, sir. Okay.
Okay, fine. So in this case, if you look into this circular balls, and they are the atom. So few atoms, you will surprise to know, and you can do it in your hand. How to do? So you just take a pure gold or a pure silver, and just you take your knife and try to slice it. You'll find at the top you'll get the few atoms at the top, because they are so ductile. You can draw it. So that this wire, don't think that it is a high technology is required. Nothing. You take a simply paper cutter, and take a wire, either indium or copper or gold, and pure gold, pure copper or pure indium. Then you slice it. You'll find that the tips are few hundred atoms or few atoms. So that is nothing but the very quantum material. So when you bring, very interesting, you will see that, you will say that sir, this is very hi-fi. No, you just go back and look to your plug in your port. You are putting, and if your plug point is a little very slack, what will happen? Your light will go deep, and if it is very tight, and it will be low. So this is the concept. The people have extended it to.
यूट्यूब लाइव होची सब ये गेले लेफ्ट मीटिंग कर देले सर आपण एकरे कोन एटा तो लाइव चली छी कोन हला कहले एटा यूट्यूब लाइव चली छी
हां ये यूट्यूब
यूट्यूब लाइव चल छी इथरे कहू जी अपन लीव कर देले
But in what range? They are compact in classical range. This is the good example around you to see that every day you are feeling the quantum phenomena in your home, that clock point. So this concept has been taken here, that we just take a very sharp tip and bring to the material, and what it will happen, and these at the bottom side is the atoms. So this electron has to pass through the barrier, basically nothing but the confinement length. It has to be passed so that it can reach to the surface, and what you can measure the current and image, or you can see your material at the nanoscale, and using the nano concept you can do it, and I'll not go to this. So these are the equipment already we have developed, and we are using these quantum effects, and tips are very small in the nanometer. If you go, you see this picture again I have taken from that book, and you will be surprised to know everybody has understood it, and I will just extend it. You see that this is nothing but your quantum mechanical barrier. Quantum mechanical barrier, same theory, it has been extended, and we have a we have an equipment, very high-end equipment, and which is very, very interesting and giving inside the atom what is happening. So that if you look into the theory, and this is your specimen, sample, the electron wave, then you have a barrier. Barrier is nothing but your, you can talk about this barrier, and I'm talking about the tip and sample, this barrier, and with this barrier, and it is coming this way. Basically, this is the current you are measuring, probe tip that you are measuring. You see, it is in the textbook, our model, long back, but today we have realized we can do. So, please, you think that nothing is written at this middle. Very interesting, the philosophy of the Dirac mathematics. Only one single concept. What he did, he said that I understand that classically what is happening in the left side and what is happening in the right side. So in all the quantum mechanical problem he could solve. He said that, okay, why are you bothered about the discontinuous point? You forget. Even if you're a plot, why are you bothered about that what is happening at exactly the quantum contact? You forget. So that's why he designed the function, see that how beautifully the simple thought, but after that what you complicated so he derived he just defined a function which just explode from left to right in this figure. Or you can say that it is again the probability. So when you are having the probability of here measuring here, and here I don't know what will be the probability, I forget. Okay, that's what this function, that is the irregular function to be solved. So if you look into that in the technology, you don't need too much. If you look into the physics formulation and so many explanations, see that the current between these two is proportional to the exponential 2 kd, and then in another observation, when any boundary comes, it will be exponential decrease or increase. So that's what it is there. It is proportional to the voltage you have applied between the tip and sample. So by taking this simple, and why the proportional and all those factors where it went, you don't require that, because while you are making the equipment, instrument, so these proportionality constant, what are the big proportional constants we are measuring, transmission probability and etc. in our textbook, those things are nothing but the intrinsic property of the equipment. So some company will make some way, some company will make in different way. So those losses can be proportional constant is nothing but losses that is zero value can be taken care. So that's why the technologist people take the fruit from the physics formulation. Okay, so you see that it is a proportionality constant is a very big thing, big parameter to calculate in the physics, but they don't bother about it. They just make the equipment and calibrate it, then can give easily the proportionality constant. It can be very high, can be very less. By using this simple equation and physics formulation, the equipment STM has been built with the quantum mechanical device. And this is another example of your quantum confinement, the quantum transportation. So if you look into that, that's what I was telling, the Nobel Prize Alfred got it by doing this. What he did, he has not done anything. What he did, he just tried to this quantum mechanical particle in a box, and he tried to do that. He was reducing this thickness, yellow color, this thickness, that at what thickness it will become a really quantum effect can it can be happen in 100 nanometer, it can be 50 nanometer, because these are the quantum. But what he was doing, he was trying to prove, okay, and reduce it where this quantum effect or the quantum confinement can observe it. That current can pass and can stop. That's all. So you are reducing it until you got it at around 20 nanometer, then it will become a very prominent equipment right now everywhere, the memory device we are using. So what happens then if you have a parallel spin, that is again it comes parallel spin, and what this non-magnetic is doing, it is the confining the electron. When it is coming, it is a delta function, that's all. Delta function, that's electron when it comes, So these act like your gate, that either electron will pass or not. So this confinement, electron confinement of this, and it is a little high physics. Basically, the electron confinement here, the energy level will decide electron will pass or not. Once it pass, again, this, if it is parallel spin, then current will be pass, and if it is anti-parallel, current will not pass. So there are the two axons, this non-magnetic layer, so two axon, and this has been developed, and your all the memory devices, if you look, and you see that these pictures are your real, if you look in the left side, this is your random access memory, we have made it parallel or anti-parallel. You see the beats are there and these connections are there, we are using in our memory devices. So this is my last example of this quantum confinement, the single electron transistor. So it is on the way, it is not been happen in the market. So if you look into that, and due to the quantum confinement, that energy level, what happens, this energy gap, and they become like the atom. Okay, they become like the atom. When you comes to the atom, molecule, then quantum dot, you see their energy levels are distinguishable, but when you come to the bulk, it is not distinguishable, continuous. That's what you get. The yellow metal is very, very prominent in the market, that is the gold, that is the yellow metal. But in case of that gold, if you reduce the size, when you make it in the quantum regime, below classical range, you find the distinguished this energy level, and this distinguished energy level also depends upon the size that you can calculate. I show you the very simple equation, and from where the particle in a box or this thing you can calculate. So that this is the proposed method, that how we can make it, and here is your this D is your nothing but the quantum, and only thing is that how you will connect these two. So now they are thinking that quantum mechanical how to connect, that is just line, otherwise our equipment is ready to be in the market. Once this equipment comes, what it will do, very simple. Now you think, if I give 1 volt, the current will pass from here. 1.5 volt, it will not pass. Listen carefully. If I give 1 volt, it will pass. If I give 1.5 volt, it will not pass. 2 volt, it will pass. What does it mean? Electrons are in the different energy level. They are not in between. So that's why this voltage will be act like 1010. That's what this your memory device. They are trying to replace it. And once this is in the market, and I think our all problems of the memory device will be solved, because only by that's what the quantum computation and the quantum mechanical device in the market. Already it is there, but this is another extension of the single electron transistor. Don't think that only one electron will travel. What I'm talking about, you have an atom, you have lots of electrons, but they are no more in the K, L, M, N, and like that. What it has happened, those electrons has come out and created different kind of the energy level, particular energy levels. That's all. Okay, so who has made it? And if you take the copper and the outermost electron only, and you know that the K electron, L electron cannot come out. Okay, so outermost electron, it is a sea of electron. They are not confined to the single atom. They combinedly they form the different levels. So that is our formulation. The people are trying to prove and already demonstrated. So they are going to bring it to the market. So let me just read out basically what I try to pass the message. So language of common men, scientists, engineers, and doctors are different. Only you have to communicate when you are talking with this. That's why we give the different books when you read, and you will see that the language how they differ from the different people. And but everybody's aim is that observation and formulation help to the society for their common uses. Then simple physics formulation to understand nature leads to big technology for serving mankind. That's what it is happening. That is physics formulation they are bringing to the market, and keep on doing the formulation. Then quantum confinement is a phenomena to understand the classical observation due to quantum effect. Classical observation due to the quantum effect. Finally, we have to observe the classical observation. I have to see my display. Okay, I have to put my hand for the scrolling my mobile. Okay, so that's what the classical observation. The quantum confinement theory helps us to design equipment to understand the nature and develop the modern equipment and the gadgets for our service. Then memory device is already, it is in the quantum confinement device, and this scanning tunneling microscopes, single electron transmission, etc. I said. Thank you very much for giving your valuable time. I don't know, I could give some message which you can carry. So these are the today's quote for you. Chaos and interaction, but no cross-link each other makes beautiful world or our material or our environment to enjoy and pass our time. So that's what we are doing. Then this is the William Wordsworth comes forth into the light of things. Let nature be your teacher. So don't forget to understand the nature so that it can guide you to even if to the small technology. So one can learn only by doing. Thank you very much. I will be happy to answer the questions if you have.
Tell us about the quantum key combination that DRDO has recently developed using optic fiber.
Oh, quantum. Okay, fine. So optic fiber, and basically what that is a different kind of development. That is nothing but this soliton. Okay, soliton. Fine. What do you mean by the soliton? Soliton is nothing but it is the quantum confined particle. Okay, quantum confined particle. That means what I am talking about. Artificially, you just sorry. Let me close and I'll tell you what they are trying to do. Okay, fine. So, may I know who has asked this question, please? Oh, okay, fine. So basically, this quantum, they have the soliton. What does it mean? Basically, they are trying to, suppose you have a different wave, they superimpose and form a big entangle which can be utilized for the communication or this thing. What it does, it is up to the 5,000 kilometer and without loss of the electron travel. So that is a theoretical or physics formulation of this quantum entangle, or you can say the quantum solution. So that's what they are trying to utilize it in the optical fiber and do it. Okay. So as I know this much about that, could I clear you? It is nothing to the quantum confinement. It is a quantum entangle. Basically, it is a quantum soliton. That is the physics formulation application to that.
Hello, sir. Can you give a brief idea about QLED, quantum LED?
Sorry, I cannot hear you.
I able to audible. It is not audible. Hello.
Yeah, now I can hear you, please.
QLED.
So, on human beings, quantum confinement is there.
Oh, very good question. Quantum confinement. Without quantum, I hope I could not pass you the message. I am talking about this. Quantum confinement means the particle will confine. We are the classical particle, classical observable. With the concept of quantum confinement, this classical observable can be explained. Okay, don't try to
Quantum
look to your body that inside me there is
Yes,
quantum confinement, definitely. Your molecule is nothing but a quantum confined
But
box.
human beings are made up of cells.
Cell is also a quantum confined of object. It has a existence, simple existence. Okay, I told you that the quantum observable, it has to be observable. If you have a observable, definitely it has been happened due to the confinement of the particle inside it. That's what it is observable. Could I make you understand?
Yeah.
If you see all the molecule, all the electrons and protons and molecules are confined in my body. That's what you are looking at me, I am existing. If they are not confined, then I cannot exist. This is the concept. Okay, so that concept we have extended when you have a quantum particle below the observable length. What happens to it? How the confinement looks like. When you have an observable particle, its confinement is continuous. That's what you cannot distinguish. Is it clear? But when its length scale is below observable, then it is this quantum particles are distinguished. I hope I make you understand.
Okay.
Hello. Sir, is there any relation? Sir, is there any relation between quantum confinement and quantization of mass?
Definitely. That is the quantization of mass of an electron. That's what we have gone extended. Electron is not a fundamental. We have called about the quark. Are you getting my point? Quark. We have defined the electron, that is nothing but the confinement of three quarks gives an electron. Is it clear?
Yes.
Then again we have confined that quark is a building blocks of neutrino, but till now we have not accepted that quark is independent. Okay, that's what we are doing this particle physics, that experiments, that how we can break the electron and realize the quark, then how we can break the quark and realize neutrino, right?
Okay, sir.
So that's what when you say the particle, that means it is definitely a quantum confinement of another particle.
Hello, sir.
Yeah.
Hello, sir. Please give an outline of QLED, quantum LED. Is it an application of this quantum confinement?
Definitely, it is a direct application of quantum confinement. I did not include it here because thank you very much to bring it. It is a direct application because it is the quantum confinement. What it happens that outermost electrons of an atom, whatever your LED material, okay, electrons, what they don't distinguish the atom, they don't sit at the atom, they come out and form the different energy level and sit. So that's what your light and guard and all are working. They are the best example of your nothing but your quantum devices.
Thank you, sir.
Is it clear?
Thank you.
Thank you.
Sir, for your nice talk. Relating to the quantum mechanics with the technology. Thank you. I request our faculty member, Professor Nitin Shah, to propose the vote of thanks. Hello. So we have reached the end of this beautiful function. Today, I take the opportunity to put my grateful gratitude into words. First of all, I would like to thank Almighty for making today's function a great success. On behalf of the college management and all students, I would like to extend my happiest thanks to our honorable chief guest, Dr. Manoranjan Kar, for his presence in the function.
Thanks
Thanks a lot
for
for
enlightening
enlightening
us
us
with
with
your
your
inspiring
inspiring
and
and
motivating
motivating
words.
words.
You are
You are
an
an
exemplary
exemplary
person,
person,
and
and
we have a
we have a
lot to
lot to
learn
learn
from
from
you.
you.
Wholeheartedly,
Wholeheartedly,
I must
I must
thank
thank
our
our
principal,
principal,
Dr.
Dr.
UC
UC
Patti,
Patti,
for his
for his
support
support
and
and
guidance
guidance
for
for
organizing
organizing
such an
such an
event.
event.
Thank you,
Thank you,
sir,
sir,
for
for
assisting
assisting
and
and
encouraging
encouraging
all of
all of
us.
us.
We have
We have
we have
we have
been
been
fortunate
fortunate
enough
enough
to get
to
the
get the
support
support
of the
of the
teachers
teachers
and the
and the
staffs
staffs
of the
of the
college
college
for
for
making this
making this
function
function
successful.
successful.
Last
Last
but not
but not
least,
least,
a
a
bouquet of
bouquet of
thanks
thanks
and
and
congratulations
congratulations
to all
to
the
all the
students
students
who got
who got
enriched
enriched
with
with
blazing
blazing
charisma
charisma
of
of
knowledge
knowledge
in
in
expense of
expense
their
of their
valuable
valuable
time.
time.
Thank you
Thank
all.
you all.
Thank you
Thank
very
you very
much.
much.
Now,
Now the meeting is over.
Thank you, sir. Thank you very much.
Thank you.
Sir, can I sign up?
ଯୋଉ ଲିଙ୍କଟା ଦେଇଛି ସେଗୁଡ଼ା ବଜେଇକି